Okay, so this video is about using Google Colab to run regressions with Python using the CPS data. If you haven't watched the video on the growth data, you should watch that because I have introduced the basics of Google Colab and Python in that video. Okay, so let's get started. Again, search Google Colab, you'll find this website. You can log in with your Gmail account and create a new notebook. Okay, once you get inside a new notebook, the first thing you want to do is to upload your data set. So go to the left-hand side, click this folder icon. After 1 second, you will see an upload icon where you can find your CPS data and upload it. Where's my CPS data? Okay. All right, so now we have our CPS data. We can close this folder file or we can leave it on. The next step we want to do is we go to our codes and install or load the packages that we need. Okay, and then you can run, you can click this run button, or you can use shift and enter or shift and return, depending on the system that you're using. Okay, so a little bit introduction about these packages. The first one is an XLRD package that is not very commonly used, and sometimes it's not updated. The problem we need that is in our previous data set, there's some issue loading the data. So we want to use that to load the data that we need to use. Okay. Import numpy as NP. Numpy is a data set. It's a package or a library that contains a lot of functions that we can use to perform mathematical operations and also to operate a lot of manipulation on an array of data. Okay, think of a feature or X variable or Y variable and a bunch of observations as a list or a line of numbers. We call it array in NumPy. Okay, so we want to use other functions in NumPy, and we don't want to call NumPy every time. So every time when we call NumPy, we'll say NP. The same with pandas. Pandas is a module or a library that contains a lot of functions that we can use to manipulate data set. And we want to call it PD so that in the future, we just need to call PD instead of its whole name. The same with stats model API, stats model formula API. These are our API or formula is sub module or sub library of the library called stats model, and API is a sub module under formula under stats model. So you can think of they are sub libraries of a whole giant library. Okay, and again, we don't want to call this long name and in the future, so we call it SMF or SM. Okay, so now you can come back and proceed with our codes. So you can copy paste and run. Okay, some people probably have an error here that is due to some broken part of this original Excel file. All right, so what you want to do is you probably want to open the Excel file, save again, and re-upload it. Okay, so I'm not going to do that. Where is my CPS data? Okay, my CPS data is here. Something is broken, right? So save it, close that, and re-upload it. Okay, let's see if it works this time. All right, so now it's uploaded. Okay, now it worked. So clearly something is broken with the original file, but it's not a big issue. So you just need to save it and re-upload it again. Maybe some broken part is fixed during that process. Okay, so DF1 is the data frame that we gave the name of. It is using a read Excel function from pandas, which we gave a nickname called PD. And we're gonna read this Excel file called cps08. And then next we want to use a function called head to see the first 5 rows of this data frame. And here are the 5 observations that we see. On the first column, we have average hourly earning of 5 different persons. We have year of these data. Clearly, they come from the same year for the first 5 observations. Column 3 is bachelor. This indicates whether this person has a college degree or not. If it's 1, then this person has. If it's 0, then this person doesn't. Female is another dummy variable that indicates the person's gender. And lastly, we also have an age variable. Okay, so another way to see this data set is using the scribe. So it will give you a summary statistic. Okay, so the scribe is a function. Okay. All right, so we have 7,711 person. This is the count of how many observations that we have for each variable. The mean of average hourly earning is around 19. The mean of year is 2008. We see no variation in year. So year is a fixed variable that doesn't give us any variation. Okay. We have 48% that has college degree, 43% that is female, and the average age is 29.57. Okay, so this is a summary statistic. Basically gives us a sense of how large is this data set, what's the distribution of each variables. Okay, so this is a nice way to take a look at your data as well when your data is huge. Okay, so come back. Let's run regressions. Before we run our first regression, we have to remember that using stats model to estimate the regression, we have to create an x0 or the constant term that I'm gonna give a name called const. It equals to 1, so the whole column will equal to 1. All right, so now if you use head, you can see that the 5 observations have everything we see before, plus an extra column that equals to 1 over every observations. This will help us estimate beta 0 in our regression, which is the intercept of the regression. All right, so now we can run our first regression. The first regression, I'm gonna call it regression 1 or reg 1. It is gonna use an OLS function from the SM module or stats models API that takes one input called endogenous variables that takes our average hourly earning as Y variable, exogenous variables that takes our age as X, and also a constant term that is used to estimate beta 0. I'm gonna call a fit function from SM to fit regression 1 which would give me the result, which I named as result 1. And then I'm gonna print out a summary function of result 1, okay? So this is what I get. This is a regression table. Beta 0 is 1.08, beta 1 is 0.6050. Okay, so that means if your age increased by 1, average hourly earning is gonna increase by 0.6 units. This is significant because t statistic is large, p-value is small, right? And you can also see all the other statistics in this table. Okay, next we're gonna control bachelor and female. So we're gonna run our second regression that, again, use ORX function from the SM module. Oops. Endogenous variable or Y variable is the average hourly earning. Exogenous variable contains 3 X variables that are bachelor, female, and age, including an extra variable called const that's gonna use to estimate beta 0. I'm gonna fit regression 2, which gives me a result, which I named as result 2. And I'm gonna print out the summary of result 2. All right, so after controlling for college degree and female, beta for age changes a little bit, right? But it is still significant because the p-value is still close to 0. All right, so this will give us some information about, do we need to control for bachelor and female? Okay. All right, so the next step is an F-test. So this F-test basically wants to test whether in this regression that uses age, female, and bachelor, whether bachelor and female combined has information or not. Okay, so we're gonna use an OLS function from the SMF module. So here, the ironic thing here is that SMF doesn't require you to add a constant term in your regression. Okay, so the OLS function from SMF module takes 2 input. The first input is, what does your regression look like? Okay, so your regression is regressing average hourly earning on age, female, and bachelor. The second input is, what does your hypothesis look like? Okay, so the second input should be, what's your data set? But once you specify results F1, you're gonna use an F-test function to test your hypothesis. That is, female and bachelor combined provide no information or provide no explanation power on average hourly earning. We're gonna name this F-test 1, and we're gonna print it out. Okay. So here we find our F-test results. That is an F statistic equals to 800, a p-value that is almost 0, a degree of freedom that contains 2 parts. So there are 2 degrees of freedom. The first degree of freedom is the degree of freedom of denominator, and the second is a degree of freedom of the number. So we don't really need to care about degree of freedom or even F statistics. What we care about is the p-value. If p-value is small enough, then we can reject our hypothesis that they provide no explanatory power. So this hypothesis is rejected because p-value is almost 0, which means that bachelor and female combined do have explanatory power on average hourly earning. All right, so that's one example of F-test. Let's continue to our regression number 3. Everything is still the same, except that now we don't control for bachelor degree. And so we get a slightly different regression results. Okay. And the last part is, can I test an F-test that tests whether age and female combined provide explanatory power? Okay, so everything is still the same, except that this is result F2 or F-test 2. I'm gonna print it out. So the F statistic is 178. This gives me a p-value that is equals to this giant thing, which is 1.8 times the natural number to the power of minus 78. So this means that p-value is almost 0 again. Okay. If p-value is so small again, I can reject my null hypothesis, which means that age and female combined do have explanatory power on average hourly earning. Okay, so that this part is basically the results that we needed for the first question in our homework. Okay, so the next half of the analysis will manipulate our y variable and convert it into log. Okay, so let's take a look at how we do it. So now I want to use a different y variable. I have to manipulate it, or I have to generate that into our data set. So I'm going to name this new column LAGE, or which means log average hourly earning, that equals to log of average hourly earning in data frame 1. This function log is borrowed from my library or my module called NumPy, which I named it as MP. Okay, so let's run this and see what happens. All right, so now we have a new column, log average hourly earning, that equals to the natural log of average hourly earning. Okay, we're gonna use this as our new y variable. Okay. Okay, so this is our regression number 4. We changed our endogenous variable into log average hourly earning from data frame 1. Our exogenous variables are the same, which is age, female, bachelor, and const from data frame 1. We're gonna print this out. We're gonna fit regression 4, and then I'm gonna print out the summary of result 4. Okay, so here you go. Now beta 1 is 0.02 versus 0.6 in our previous regressions. So we have to interpret this differently because our y variable now is log average hourly earning. So we have to interpret it as 1 unit change in age, how much percent change in average hourly earning, instead of how much unit change in average hourly earning, right? So in a log linear model, this should be interpreted as 100 beta percent, okay? So this should be interpreted as 2% or 2.73% increase in average hourly earning when you increase age by 1 unit, okay? The next step is, what if you use LogAge instead of age? So you should use the NumPy module again, using the log function from the NumPy module to create a new column that is LogAge. Again, we're going to use the head function to see what happens for the first 5 observations. All right, so this is what we get. We get a new column, LogAge. It is the natural log of age. Now we can run a new regression, which is regression number 5. That takes log average hourly earning from data frame 1 as y variable. And it takes log age, female, bachelor, and const from data frame 1 as X variables. Okay, so the only thing that differentiated this new regression is that I'm using LogAge. We're gonna run this and print it out. Now LogAge, the coefficient here becomes 0.8. So how do we interpret this again? Because this is a log function. So 1% increase in age will lead to 0.8% increase in average hourly earning, because this is a log model. So 1% increase in X variable, beta 1% increase in Y variable. Okay. The next question is on a scenario that is what happens what happened to percent change in average hourly earning if you increase age from 35 to 36. So here, because in the regression you are using log age, so you have to convert 35 and 36 into log 35 and log 36. You're going to use the function from numpy, the log function from numpy. The reason why I times 100 here is because in the problem set, it asks for percentage. Okay, if it doesn't ask for percentage, then you don't need to times 100. Okay, so the idea is that from age 35 to 36, there's a certain percentage change in age. So that converts to 2.26% increase in average hourly earning. The next part uses a quadratic form of age. So first we have to generate an age square. Okay, so using this, we created a new column that equals to age square. Now let's run regression 6 that contains age and age square and other control variables like female, bachelor. Be careful that here we are using average hourly earning as our Y variable. Okay. There is a confusion whether age and age square are useful combined. So you can use an Ftest to do that. You specify a regression that is average hourly earning on age square, female, and bachelor. Your hypothesis is that age and age square combined doesn't provide any explanatory power. You use OS regression from SMF module, and you use an Ftest function from the SMF module to test your hypothesis. And finally, you print it out. You get this 130 as your F statistics, and you get this giant thing that is almost 0 as your p-value. So p-value is so small, then your null hypothesis is rejected, which means that age and age square combined do have explanatory power. The next part, you're gonna employ a interaction model. So this interaction is between age and female. First of all, you have to create this column that is age times female. Okay. For the first 5 rows, because the first 5 rows are all male, so age times female for the first 5 rows are all 0. But if you go under, you'll find values that are non-zero. In this case, you run this regression 7 that uses log average hourly earning as Y variable, age times female, and bachelor as your X variable, along with constant term. Okay, if you print it out, you can see that all the variables are significant because all of them has very small p-value. Okay. And the last part, age and bachelor's interaction. Okay. So now you created an extra column that is the interaction of age and bachelor. And you can run the regression of that. Okay, so this is basically what we need to interpret all the results that we use CPS data in our homework.